Hello, I am Barry Ryan, a PhD student from the University of Edinburgh, and welcome to my presentation. Today I will discuss my research topic titled Multi-Omic Graph Diagnosis, MOGDx, a tool for the integration and classification of heterogeneous diseases. This project was supervised by Dr. Ian Simpson and Dr. Riccardo Marioni. In this project, we hope to classify heterogeneous diseases by integrating multi-omic measures. Heterogeneity in human diseases refers to the variability and diversity observed among individuals affected by a particular condition. Heterogeneity can pose many difficulties. For example, in clinical trials or treatment strategies, heterogeneity may lead to varying responses to therapies, making it challenging to determine the most effective approach for all individuals. It can also complicate the identification of biomarkers, diagnostic criteria, and the development of targeted therapies. To address these challenges, we strive to classify and stratify diseases based on specific characteristics, such as genetic markers, biomarkers, or clinical subtypes. This allows for more precise diagnoses and targeted treatment approaches tailored to individual variations within a heterogeneous population. The development of omic technologies has provided us with an opportunity to use artificial intelligence to embrace this heterogeneity and use it to provide valuable insights into disease mechanisms, treatment responses, and personalized medicine. Hence, we propose MOGDx, a tool which uses a network taxonomy to integrate multi-omic measures and a graph neural network for heterogeneous disease classification. MOGDx is a tool which can be run on the command line and consists of 4 key concepts. A patient similarity matrix is a computational framework that represents the similarities and relationships between patients based on various features or characteristics. We constructed our patient similarity matrix from the most predictive features of each omic measure. The k-nearest neighbors algorithm was then used to construct a network for each omic measure, and these networks were integrated using similarity network fusion. Similarity network fusion is a computational method of network integration, which leverages the strengths of each network, capturing complementary information and improving the accuracy and robustness of analyses. The fused patient similarity network is needed to be augmented with node features for graph neural network training. We augmented our nodes with a compressed representation of all omic measures using an autoencoder. An autoencoder consists of an encoder that compresses high-dimensional input data into a lower-dimensional representation, and a decoder that reconstructs the original input from the compressed representation. By training the autoencoder to minimize the reconstruction error, it learns a compact representation that captures the most salient features of the input data. One autoencoder per omic measure is trained, and the compact representation of each modality is concatenated into a single node vector. A graph neural network is a type of neural network architecture designed to process and analyze data structured as graphs. It leverages graph-specific operations to propagate information through the graph structure and learn from both graph structure and node features. We implemented a graph convolutional network for node prediction tasks. Cancer is considered a heterogeneous disease due to the presence of significant variation among different tumours, even within the same type of cancer. This heterogeneity can be observed at various levels, including genetic, molecular, cellular, and clinical characteristics. We benchmarked the performance of MOGDx on 3 cancer datasets from the Cancer Genome Atlas, namely PAM50 subtype classification for breast-invasive carcinoma, tumour grading in lower-grade glioma, and subtype classification in the pancreas-kidney cohort. MOGDx is more flexible than comparable methods. It is able to accept any number of modalities and performs imputation to ensure full patient coverage. The performance of MOGDx was superior or comparable to previously published methods, while including more modalities and more patients than previously published methods. The flexibility of MOGDx allows us then to ask such questions such as, are more modalities better, and how do individual components of MOGDx perform? To investigate this, we analysed how accurate individual omic measures are and what is the optimal combination of omic measures. Clearly, when treating omic measures individually, some omics perform better than others depending on the classification task and the dataset analysed. We favour measures which have a greater patient coverage, as accuracy can be inflated if subsetted to a smaller number of patients. Overall, we found that integrating more omics is better, as a similarity network fusion integration is able to preserve similarity within an omic measure, as well as complementing this with strong relationships from other measures. The converse to this was the lower grade glioma dataset. where one omic measure was significantly more accurate than all other measures, and including the other measures added too much noise and reduced the accuracy. We also performed ablation experiments to analyse the individual components of the MOGDx architecture. The patient similarity network only model was trained by one-hot encoding each node feature, thus allowing the graph neural network to only learn from network structure. The autoencoder only model was trained by removing all edges from the patient similarity network. The results highlight the predictive power of the patient similarity network, including the lower dimensional representation of each omic measure from the autoencoder reduces the susceptibility of the graph neural network algorithm to splits in the dataset, resulting in a more reliable and robust results. In summary, this research demonstrates the use of network integration and graph neural network classification algorithms for heterogeneous disease classification. There is no one-size-fits-all solution to heterogeneous disease classification. However, we show that patient similarity is a powerful measure for disease classification, as well as the importance of flexibility when it comes to integrating omic measures. Thank you for your time.